All right, starting with number 1. Given the region below, we have the natural log of x minus 3, that's the curve here, and then the 7 minus 1/4 x, that's the linear graph, and the x-axis. So you can see that enclosed region. I meant to say find the area. So I think we always want to maybe explore top minus bottom first, which is fine. So if we do top minus bottom, the issue is that there is a change at this intersection, right? At this intersection, the top function is going to be different on one side versus the other side. So you see that on the left side, the top function is going to be that natural log graph. On the other side, it's going to be that 7 minus 1/4 x graph. Okay, so we need 2 separate definite integrals. Okay, use your calculator as well to find these intersections. You can, if you're using your graphing calculator, you can find the intersection. Well, here you're going to be using zeros, second trace 0, and here be second trace intersect. Okay. But if you're using a graphing calculator, or sorry, if you're using a scientific calculator, you can do numsolve. Numsolve between natural log of x minus 3 and 0. And then numsolve between natural log of x minus 3 and 7 minus 1/4 x. And then numsolve between 7 minus 1/4 x and y equals 0. Now, if you see a graph that, if you can't see quite the entire graph, you can zoom out, or you can do this. You can go to Windows, and then just adjust your x min, x max, y min, y max. You can just take allow the graph to show you more. So in this case, looks like you want to see more of the right of the graph. So if you want to play with the graph, just play with these 4 numbers here: x min, x max, y min, y max. That will just extend your x or y axis. Here, I want to extend my x-axis a lot more to the right, so just choose a large number, do 40, 30, and you can see a lot more of the. So that's all we need, right? We just want to find that intersection, allow us to see that intersection. So if you do second trace intersect, so intersection, I'm looking for the intersection between the curve and the line. Choose a point close to the intersection. Okay, don't choose directly on it. Close to it, hit enter. And now the cursor should be blinking on the other graph. Choose a point close to that intersection, hit enter a 3rd time, and that'll get you that intersection, 17.346. If you want to find the x-intercepts, you can do second trace, and then you're going to choose 0. So you're looking for a 0. So now I'm choosing points on the same graph. I'm just choosing points on either side of the x-axis. So I'm going to choose a point to the left or below that x-intercept, hit enter, and then scroll to the right to choose a point on the other side of the x-intercept, hit enter a 3rd time, and you get 4. Okay, you do the same thing for the other point here, and you get 28. You can also solve this by hand. 7 minus 1/4 x equals 0. Yes?
When you do this on the TI-36X, when you're making these functions, the intersection, it gives sign.
Yeah, so what that means is you have to choose you have to let it start at a point that exists on the natural log graph. So you may want to let it start at like 5 or 4, but you don't want to start at 3 or 0, because then that's going to make that natural log undefined. Yeah, so if you start at a number to the right of 3, like even 3.1, that will get you to 4. Okay, so here's our area formula. Definite integral from 4 to, this is intersection 17.346. Top minus bottom, the top of my rectangle is hitting the natural log, the bottom is hitting the 0. And then second definite integral, 7 minus 1/4 x minus 0 from 17.346 to 28. Use your calculator. Okay, if you pick up the answer key, you can also do right minus left. So you can convert your equations to be in terms of x, and then all you need would be one definite integral, and you will go from 0 to the highest y value, which is 2.263. Okay, but I'll leave it as top minus bottom for now. Either method is fine. Okay, any questions with one? Okay, number 2, given the enclosed region, you got natural log of x plus 6. You have the y equals -3. You have x equals 5. Find the volume of the solid generated revolving around the line y equals -4. So -4 is a little below that -3, so it's going to be down here. Now I drew the x and the y axis as frame of reference, but it's not going to play a role at all for your shaded region. Okay, you're just going to basically, you're just looking at the boundaries. So the ones, whatever is inside the boundary is just not going to matter at all. Okay. Okay. X and y axis here do not play a role. Okay, so look at where that axis of revolution is. Is this disk or washer method? What do you guys think? We only do disk if the axis is what? Is up against the flat surface of the region. It's got to be not only touching it, but it's got to touch every point of the shaded region for that side. We don't see that's the case, right? There's a gap, there's a hole. So this is going to be washer method. So we need 2 radius. Okay, one radius that extends from the dotted line to the furthest boundary. And then we need a radius that extends from the axis to the closer boundary. Big R and little r. Top minus bottom. Top of the big radius is sitting on the natural log. The bottom is sitting at the -4. And little radius is top minus bottom. Top is sitting at the -3, the bottom is sitting at -4, so -3 minus -4. Okay, we also need to spend the time to find that intersection. So you can set natural log of x plus 6 equal to -3. And again, make sure that you choose a value. Actually, this should be safe. Yeah, you can start at 0 and you'll be able to get that intersection there. Okay, let me know if you have any trouble finding intersections on your calculator or finding bounds in your calculator. Okay, ready for the volume formula. Left bound to right bound, right? Everything's in terms of x. Make sure that you're squaring your radius separately. Okay, practice entering into your calculator. Let me know if something doesn't, if you're running into any issues. Okay, next page. Same shader region. Okay, got the natural log of x plus 6. You have the y equals -3. You have x equals 5. But now you're rotating around the line x equals 5, which is same as this boundary. Okay, so now what does this look like to you? Disco washer. This method. You see how that dotted line is up against the flat surface? There's no gap, there's no hole. It's touching every part of that surface on this side. So as this rotates, all we need is one radius. Okay, but the difference there is that the radius has to be perpendicular, so got to extend horizontally. Anytime you see a horizontal radius, that's a hint that your equation needs to be rewritten. These equations are built for top minus bottom, not quite for right minus left. So we have y equals natural log of x plus 6. I need to solve for x. To solve for x, I need to get that natural log to go away. We can involve its inverse, so we can raise both sides with e as the base. And solve for x. That's the curve here. Okay, this line is x equals 5. Big radius, 5 minus parentheses. Okay, make sure you put the parentheses. Otherwise, without the parentheses, you may forget to distribute the negative through. Oops, I'm sorry, my bad. X is e to the y minus 6. All right, I messed that up. Okay, so we have our big radius. The only thing missing now is we need the bounds. The bounds has to be in terms of y. So we're stacking these disks from the lowest to the highest y value. So the lowest y value is -3, but the highest y value is going to be whatever this point is, right? So we know that this is part of the natural log graph. We know the x value here is 5, so I can just enter 5 in for x and figure out what that y value is, right? So this y value at this point is natural log of 11, so that's going to be the highest of my boundary here. You can do natural log of 11, or you can find a decimal approximation. So there's no need to graph and look for intersections. Just simply plug 5 into the natural log graph and look for that y value, and that's all you need. Okay. Anytime there's rotation, whether it's disk or washer, you'll see a pi coefficient in front. Okay. But just be careful that you're not just randomly using pi for area or for cross-section. Okay. Most area and cross-section problems are not going to have pi unless it's cross-section with semicircles. You can say natural log of 11, or you can say 2.398 as indicated on the key. Okay, number 3. Any questions so far? Okay, so here we have e to the x plus 1. You have the square root of x plus 6. Okay, rotating around the line x equals -6. Okay, clearly off the graph, this is going to be washer method. Okay, extend your radius from the axis to the furthest boundary that you can find. And then from the axis to the closer of the two boundaries. Now, anytime you see horizontal radius, you know your equation has to be rewritten in a more usable form. Solve for x, so square both sides. Here, I want to isolate that e to the x by itself first. I want to get that exponent down. I can involve natural log, take the natural log on both sides. That x can now freely come down. Natural log of e just goes away, becomes 1. Okay, right minus left. Right endpoint for my big radius is sitting on the natural log. Left endpoint is sitting at -6, so right minus left. Little radius, right endpoint is sitting on the y squared minus 6. Left endpoint is sitting at the -6. Okay, find the intersections using your graphing calculator. You can also find the intersection using your numsolve, using numsolve on your scientific calculator. Now, once you find, let's say you did it in terms of x. If you did it in terms of x, you could do it again in terms of y, but as soon as you find the x values, you can just enter in these x values into either the original equation and then plug in, and then you can find the y value that way as well. But you could do numsolve from both perspectives, and that would be fine as well. So whichever way you're comfortable with. Now notice that we are stacking these circular rings from the lowest to the highest y values here. So we're looking at y values from 1.007 to 2.536. Okay, any questions with 3? (3A). Okay, go to 3B. Same shaded region, so a lot of information you can just carry over. Okay, this is a cross-section problem. This is a parallel to the y-axis, so the y-axis is this direction, parallel to it, so we're going to stay in that vertical orientation. So the base is just going to connect from one boundary to the next. No rotation here. Top minus bottom. Top is sitting at the square root, and bottom is sitting at the e to the x plus 1. Careful. Use a set of parentheses to protect that bottom function there. Okay, let's build our area. It's an isosceles right triangle with hypotenuse on the base. You know, most of your formulas will be base squared. The only difference is what's out in front. This is going to be 1/4 base squared. Top minus bottom, so we only care about the x values at these intersections. No pi, no rotation, okay? Just enter all that in the calculator. Okay, last one, number 4. You have a parabola and a linear graph. Find those intersections. But first, let's see here. Rotating around the line y equals 4. Y equals 4 is going to be touching the graph, touching that shaded region. Okay, what is this going to be here? Disk or washer method? Washer, good. I think a lot of students do this. They see that their reasoning for this method is that it's touching the graph. So it's touching the graph, true, but you see how there's all this gap that we still have to account for. So unless it's up against a flat surface, touching and across the flat surface, you're not going to be able to say it's this method. Okay, so just because it's touching, we still got to use washer method because there's still gaps here. Okay, so we need to find 2 radius. Okay, so from the axis of revolution, we extend to the furthest boundary to create our big radius. Okay, from the axis to the closer boundary will be your little radius. And we do top minus bottom. Top of the big radius is sitting at the dotted line, the 4. The bottom of big radius is sitting at the linear graph, -1/2 x plus 2. Make sure you put a set of parentheses there to protect that. Right, top is sitting at the 4. The bottom is sitting at the -x² plus 4. Okay, find your boundaries here. You only care about the x values. Okay, any questions? Come around to see if you guys need any help. Right, so y-axis is so parallel. So when you see that that the highest point is simply if you know what the x value is at any point, you can always just plug that x value in. For where the highest Y value means.
Oh, here it's talking about the highest Y value.
You guys pick it up, right? 'Cause you have to plug it in.
The highest Y value you can tell is that there's no line. So there's no 30. You know the highest Y value. Most Y value is energy.
Yeah,
I mean, it was like.
I didn't know it.
Oh, okay. Because then you know that your right boundary is your left boundary is going to be whatever that is.
It's in the middle of the class.
So then you'll do intersection Y at that point.
And I had, and it's gross like this.